Tonight, we're going to explore one of the most unsettling journeys humanity could ever attempt. The journey to escape the Milky Way. There are roughly 100 billion to 400 billion stars in our galaxy. The Milky Way stretches about 100,000 light-years from one side to the other. Our solar system sits roughly 25,000 light-years from the galactic center, buried inside one of the galaxy's smaller spiral structures. And even light, the fastest thing in the universe, would need 100,000 years to cross the galaxy from edge to edge. Given those numbers, escaping the Milky Way should feel like a simple problem of distance. Build a fast enough spacecraft, aim it outward, give it enough time, and eventually, it should leave. Yet instead, the deeper you look, the stranger and more disturbing the journey becomes. Because escaping the Milky Way does not simply mean flying away from Earth. It does not simply mean passing Pluto, or crossing the outer edge of the solar system, or drifting beyond the last familiar planets. It means breaking free from the gravity of the entire galaxy. The stars, the gas, the dust, the central bulge, the invisible dark matter halo surrounding it all. It means leaving the system that has carried the Sun, Earth, and every human life through space for billions of years. And by the end of tonight, you're going to understand why that might mean the most terrifying departure humanity could ever make. Because the Milky Way is not just the backdrop of our night sky. It is the structure that holds our entire cosmic home together. Every star you have ever seen with your eyes belongs to it. Every constellation humans have named, every ancient story written into the sky, every point of light used by sailors, farmers, astronomers, and dreamers, all of it is part of the same galaxy. To escape it would mean leaving behind the only cosmic environment humanity has ever known. The journey would begin on Earth, on a small rocky planet orbiting one ordinary star. From there, a spacecraft would have to leave the atmosphere, escape Earth's gravity, pass the Moon, cross the planetary system, move beyond the outer planets, and keep going far past the region where the Sun still feels like the center of everything. But even that would only be the beginning. Voyager 1 has already crossed into interstellar space, and it is the most distant human-made object ever launched. Yet compared with the full scale of the Milky Way, Voyager has barely moved. It has traveled beyond the protective bubble of the Sun, but it has not come close to leaving the galaxy. It is still inside the same immense rotating system as Earth, still traveling within the same stellar island, still bound to the Milky Way's long, invisible pull. That is the first unsettling truth. You can leave the solar system and still be nowhere close to escaping the galaxy. The Milky Way is so large that ordinary ideas of travel begin to collapse. A distance that feels enormous to us. 1 billion miles, 10 billion miles, even 1 trillion miles, becomes almost meaningless on the scale of a galaxy. The nearest stars are already separated by light years. The galaxy itself is tens of thousands of light years across. And beyond its bright spiral disk, its gravity keeps reaching outward through a vast halo we cannot see directly. So the real question is not simply how far a spacecraft must travel. The real question is what it would actually take to become free. Because right now, Earth is not sitting still inside the Milky Way. The Sun is not sitting still. The entire solar system is already racing around the galactic center at a speed that would seem almost impossible by human standards. And yet, even at that speed, we are still trapped inside the galaxy. To escape a galaxy, a spacecraft has to do something more exact than simply travel far away. It has to become gravitationally unbound. That means it must move fast enough and far enough that the Milky Way can no longer pull it back into a long orbit. If the spacecraft is too slow, it can travel outward for thousands or even millions of years and still remain part of the galaxy system. Its path may stretch wider and wider, but gravity will keep curving that path through space. This is the same basic idea behind escape velocity. On Earth, escape velocity is about 11.2 kilometers per second. That is roughly 40,000 kilometers per hour. A rocket that reaches that speed, it can leave Earth's gravity behind, assuming it is moving in the right direction and does not lose too much energy to the atmosphere. Below that speed, it may still fly high above the planet, but it eventually falls back or settles into orbit. Around the Sun, the numbers become larger. At Earth's distance from the Sun, solar escape velocity is about 42 kilometers per second. That is the speed needed to break free from the Sun's gravity at our orbital distance. The planets, asteroids, comets, and spacecraft inside the solar system are all moving inside that wider gravitational field. But the Milky Way is larger than both of those systems by almost absurd amounts. The Earth is about 12,700 kilometers wide. The solar system, if you measure out toward Neptune, spans several billion kilometers. The Milky Way spans about 100,000 light-years. 1 light-year is about 9.5 trillion kilometers. The distance light travels in 1 year. So the galaxy is a structure measured in hundreds of thousands of trillions of kilometers. And gravity fills that entire structure. The Milky Way is made of stars, gas, dust, stellar remnants, clusters, nebulae, and a dense central region, where stars orbit around a supermassive black hole called Sagittarius A star. That black hole contains about 4 million times the mass of the Sun. It sounds enormous, and it is, but it is only one part of the galaxy's total gravitational structure. The galaxy's visible matter is already massive. It contains somewhere around 100 billion to 400 billion stars. Many of those stars are red dwarfs, small cool stars that can shine for hundreds of billions or even trillions of years. Others are larger sun-like stars, white dwarfs, neutron stars, and black holes left behind after massive stars died. Between those stars is interstellar gas and dust. Some of it is spread thinly through space. Some of it gathers into giant molecular clouds, cold, dark regions where new stars can form. These clouds can span dozens or hundreds of light years and contain enough material to make thousands of stars. All of this contributes gravity. But the strangest part is that most of the Milky Way's mass appears to be invisible. Astronomers know this because the galaxy rotates too quickly. If the visible stars and gas were the only mass holding the Milky Way together, the outer stars should move more slowly, or some of them should drift away. Instead, stars far from the center still orbit at high speeds. Something unseen is adding gravity. That unseen mass is called dark matter. Dark matter does not glow, reflect light, or absorb light in any ordinary way. We detect it through its gravity. Around the Milky Way, it seems to form a vast halo, extending far beyond the bright spiral disk we see in images. So a spacecraft trying to escape the galaxy would have to escape more than the starry part. It would have to climb out of an invisible gravitational well surrounding the galaxy itself. That is what makes the idea so much larger than simply flying outward. A spacecraft could pass beyond the planets and still belong to the Sun. It could pass beyond the Sun's protective bubble and still belong to the Milky Way. It could travel through interstellar space for ages and still be moving inside the galaxy's gravity. Real escape means crossing the point where the spacecraft's motion is no longer part of the Milky Way's long hold. And that is where the journey becomes unsettling. Because Earth, the Sun, and every planet in our solar system are already moving through the galaxy at tremendous speed. And even that speed is still only orbit. The Sun is already moving faster than almost anything humans have ever built. Right now, the entire solar system is orbiting the center of the Milky Way at roughly 500,000 miles per hour. That is about 220 kilometers per second. At that speed, you could cross the distance from New York to Los Angeles in less than a minute. You could circle Earth in under 3 minutes. You could travel the distance to the Moon in less than half an hour. And yet, on the scale of the galaxy, this is normal motion. Earth does not simply orbit the Sun while the Sun sits still. The Sun carries Earth, the Moon, Mars, Jupiter, Saturn, every asteroid, every comet, and every spacecraft along with it as it moves around the galactic center. The entire solar system is like a small family of worlds being swept through a much larger cosmic current. The path is enormous. The Sun sits about 25,000 to 27,000 light-years from the center of the Milky Way. A light-year is the distance light travels in 1 year, about 9.5 trillion kilometers. So even though the solar system is moving at 500,000 miles per hour, the circle it has to travel is so large that one full orbit takes roughly 225 to 250 million years. This is sometimes called a galactic year. 1 galactic year ago, Earth was in the age of the dinosaurs. The first dinosaurs were spreading across the planet. The Atlantic Ocean was only beginning to open. The continents were arranged very differently. There were no humans, no birds as we know them today, no flowering grasslands, no cities, no telescopes, no rockets. Since the Sun was born about 4.6 billion years ago, it has completed only about 18 to 20 trips around the Milky Way. That means the entire history of Earth fits into a small number of wide, slow loops around the galactic center. The strange part is that we do not feel any of this. Standing on the ground, Earth feels still. The night sky looks fixed enough that ancient people could build calendars from it. Farmers used the rising and setting of stars to track seasons. Sailors used constellations to cross oceans. For thousands of years, the sky seemed like a stable ceiling above human life. But every moment, Earth is rotating once every 24 hours. It is orbiting the Sun at about 30 kilometers per second. The Sun is orbiting the Milky Way at about 220 kilometers per second. And the Milky Way itself is moving through the local group of galaxies, slowly falling toward Andromeda. Nothing is still. The reason the stars appear steady is that they are so far away, and human lives are so brief. The nearest star system, Alpha Centauri, is more than 4 light-years away. Many of the bright stars in familiar constellations are dozens, hundreds, or thousands of light-years distant. Over one human lifetime, their motion is usually too small to notice without precise instruments. Over hundreds of thousands of years, the constellations change. The Big Dipper will stretch and deform. Orion will lose its familiar shape. The stars that seem fixed tonight are all moving on their own paths around the galaxy, each with its own speed and direction. The Milky Way is less like a still painting and more like a vast rotating storm of stars. The solar system is part of that storm. It is moving fast enough to circle the galaxy, but not fast enough to leave it. Its path is curved by the combined gravity of the galactic disk, the central region, and the dark matter halo surrounding everything. The Sun is racing forward, but its speed is balanced by gravity. The same way Earth's orbital speed is balanced by the Sun's pull. That is why 500,000 miles per hour is still a form of captivity. It sounds like escape, but it is only orbit. To truly leave the Milky Way, a spacecraft would need a different kind of motion. It would need enough speed to stop following the galaxy's curve and begin climbing away from it forever. To leave the Milky Way, distance is only part of the problem. The deeper problem is speed. Near the Sun's position in the galaxy, the escape velocity from the Milky Way is estimated at roughly 550 kilometers per second. The exact number changes depending on how astronomers model the galaxy's mass, especially the dark matter halo. But the basic scale is clear. A spacecraft would need a speed of hundreds of kilometers every second to become unbound from the galaxy. That is difficult to picture, because human travel speeds are usually measured in kilometers per hour or miles per hour. A passenger jet moves at about 900 kilometers per hour. The International Space Station orbits Earth at about 28,000 kilometers per hour. Earth orbits the Sun at about 107,000 kilometers per hour. Voyager 1, after using gravity assist from Jupiter and Saturn, is moving away from the Sun at about 17 kilometers per second. That is fast enough to cross the width of the continental United States in a few minutes. But compared with galactic escape velocity, it is slow. 550 kilometers per second is more than 30 times Voyager 1's speed relative to the Sun. And because kinetic energy grows with the square of speed, going 32 times faster does not require 32 times more energy. It requires over 1,000 times more energy for the same amount of mass. That single fact changes the entire journey. A tiny probe is already hard to accelerate. A crude spacecraft, with shielding, fuel, air, water, food systems, spare parts, radiation protection, power plants, and living space, would be far harder. Every kilogram matters. Every wall, every tank, every cable, every storage container adds to the total mass that has to be pushed to escape speed. This is why spaceflight becomes so unforgiving. On Earth, if you want a larger ship, you build a larger engine. In space, a larger engine usually needs more fuel. More fuel adds more mass. More mass requires even more fuel. This is the rocket equation, the basic mathematical rule that makes high-speed space travel so difficult. It says that the fuel needed to change a spacecraft's speed rises brutally as the desired speed increases. For ordinary missions, gravity assists can help. Voyager 1 used Jupiter's gravity in 1979 and Saturn's gravity in 1980 to gain speed and change direction. A gravity assist works because a spacecraft steals a tiny amount of orbital energy from a planet. The planet slows by an immeasurably small amount, and the spacecraft leaves faster than it arrived. But planets can only give so much. Jupiter is massive, more than 300 times Earth's mass, and it orbits the Sun at about 13 kilometers per second. Saturn is also enormous, and its gravity helped place Voyager 1 on a path out of the planetary system. These maneuvers were brilliant, but they did not give Voyager anything close to galactic escape speed. The Milky Way's gravity is a much larger prison. A useful comparison is throwing a stone from Earth. Toss it gently and it falls back. Throw it faster and it travels farther before returning. Fire it fast enough, at about 11.2 kilometers per second, and it escapes Earth completely. It no longer follows a path that brings it back to the ground. The same idea applies to the galaxy. Only the object being escaped is not a planet beneath your feet. It is a rotating system of hundreds of billions of stars, clouds of gas and dust, a dense central region, and a dark matter halo extending far beyond the visible disk. A spacecraft trying to escape would be climbing out of that entire gravitational well. And the direction matters. Moving with the galaxy's rotation is different from moving against it. Moving outward from the galactic center is different from moving above the disk. A spacecraft would need its speed arranged in the right way relative to the Milky Way, so that its path does not curve back into a long galactic orbit. That is the unsettling shift. The journey is not simply about crossing 100,000 light years. It is about gaining enough energy to stop belonging to the Milky Way. And when we compare that requirement to the machines humanity has actually built, the scale of the problem becomes much colder. Our fastest deep space travelers are not waiting near the edge of escape. They are still crawling inside the galaxy. The spacecraft that shows this most clearly is Voyager 1. Voyager 1 launched from Cape Canaveral on September 5, 1977, riding into space on a Titan IIIe rocket. It was built for a very different mission. Its first job was to visit Jupiter and Saturn, study their atmospheres, moons, magnetic fields, and rings, then continue outward after its main planetary work was done. It was not designed to escape the Milky Way. It was not designed to reach another star. And yet, after nearly half a century of travel, it remains one of the greatest long-distance machines humanity has ever sent into space. Voyager 1 used gravity assist from Jupiter in 1979 and Saturn in 1980. These encounters changed its speed and direction, placing it on a path that carried it upward and outward from the plane where most planets orbit. In 2012, it crossed the heliopause, the boundary where the sun's solar wind gives way to interstellar space. That made it the first human-made object to enter the space between the stars. But its speed is about 17 kilometers per second relative to the sun. That is roughly 38,000 miles per hour. By human standards, this is astonishing. It is faster than a rifle bullet, faster than any aircraft, faster than anything built for travel on Earth. At that speed, Voyager 1 could cross the distance from Earth to the Moon in about 6 hours. it could cross the diameter of Earth in about 12 minutes. It could travel from the Sun to Earth in a little over 100 days. But the galaxy is built on a different scale. The nearest star system, Alpha Centauri, is about 4.3 light years away. That is roughly 40 trillion kilometers. At Voyager 1 speed, reaching that distance would take more than 70,000 years. That is longer than recorded history, longer than agriculture, longer than the time since humans began building permanent towns. And Alpha Centauri is only the nearest neighboring star system. It is not the edge of the galaxy. The Milky Way is about 100,000 light years across. If Voyager 1 could somehow keep moving in a perfectly useful direction, and if nothing changed its course, crossing a distance like that at its current speed would take hundreds of millions of years. And even that simple comparison does not fully solve the problem, because escaping the Milky Way is not just about crossing the disk. It is about becoming unbound from the galaxy's gravity. Voyager 1 is not close to that. It has left the Sun's protective bubble, but it has not left the galaxy's gravitational system. It is still traveling inside the same vast stellar structure as Earth. It is still deep inside the Milky Way, surrounded by the same galactic disk, the same dark matter halo, the same long gravitational field that holds the Sun in its orbit. This is why Voyager feels so strange as a comparison. In human history, it is almost impossibly far away. Its radio signals take many hours to reach Earth. Its power comes from plutonium-238, slowly decaying inside radioisotope generators. Its computers were built with technology from the 1970s, yet it has traveled farther from Earth than any other spacecraft. But compared with the Milky Way, it has barely begun. It is less like a bullet fired out of the galaxy, and more like a seed drifting away from one tree inside an endless forest. The seed has left the branch. It may even have left the shadow of the tree, but the forest still stretches around it in every direction. The same is true for every deep space probe humanity has launched. Pioneer 10, Pioneer 11, Voyager 2, New Horizons. All of them are remarkable machines. All of them are leaving the planetary region of the solar system. Some will drift through interstellar space for millions or even billions of years if they survive impacts with dust. But none of them are true galactic escape craft in the dramatic sense. They are not moving at hundreds of kilometers per second. They are not aimed with the purpose of breaking free from the Milky Way. They are quiet relics, coasting through the galaxy, still bound to the same cosmic island that made them. So if humanity ever wanted to build a spacecraft that could actually escape the Milky Way, it could not simply copy Voyager and wait longer. Waiting would stretch the journey beyond useful human meaning. A real attempt would demand engines, power systems, and mission designs far beyond anything currently flying. The problem is no longer how patient we can be. It is how fast a machine can be made to move. The engines that carried humanity into space were built for a much smaller problem. Chemical rockets are powerful enough to lift a payload from Earth, climb through the atmosphere, and reach orbit. They burn fuel and oxidizer together, creating hot gas that blasts out of the engine nozzle. The faster that gas leaves the engine, the more push the rocket gets. This works well for launching from a planet. The Saturn V rocket, which carried Apollo astronauts to the Moon, burned kerosene and liquid oxygen in its first stage. The space shuttle used liquid hydrogen and liquid oxygen in its main engines. Modern rockets, like SpaceX's Falcon 9 and Starship, still depend on chemical propulsion, using fuels such as kerosene or methane mixed with liquid oxygen. These engines are extraordinary machines, but their exhaust speeds are only a few kilometers per second. For reaching orbit, that is enough. For escaping the Milky Way, it is painfully small. A spacecraft trying to become unbound from the galaxy near the Sun's position would need a speed measured in hundreds of kilometers per second. Chemical rockets can help start a mission, but they cannot efficiently push a large spacecraft to that kind of speed. The fuel burden becomes overwhelming. The rocket equation closes in. More speed requires more fuel. More fuel makes the spacecraft heavier. A heavier spacecraft requires still more fuel to accelerate. This is why engineers begin looking at stranger ideas. One of the most dramatic is nuclear pulse propulsion. In the late 1950s and early 1960s, Project Orion studied the idea of using nuclear explosions to push a spacecraft forward. The concept was blunt but powerful. Drop a nuclear device behind the spacecraft, detonate it, and let a massive shock absorber plate catch part of the blast. Do this again and again, and the spacecraft could build up speed far beyond ordinary rockets. On paper, it offered enormous thrust. In reality, it meant building a ship that survived repeated nuclear detonations behind it. It also meant handling radiation, political restrictions, launch safety, and the practical problem of carrying hundreds or thousands of nuclear devices. The idea remains one of the clearest examples of how extreme propulsion becomes when ordinary rockets are no longer enough. Fusion propulsion is more elegant. Fusion is the process that powers the sun. Light atomic nuclei, usually forms of hydrogen, combine into heavier nuclei and release energy. A fusion spacecraft would use that energy to push high-speed particles out the back of the engine. The fuel could be isotopes like deuterium and helium-3, or other fusion mixtures. The potential efficiency is far beyond chemical rockets. But controlled fusion itself is still one of the hardest engineering problems on Earth. Fusion fuel has to be heated to extreme temperatures, often hotter than the core of the sun, and confined long enough for useful energy to be produced. Doing that inside a compact, reliable spacecraft engine that can run for years or decades is far beyond current capability. Antimatter is even more extreme. When matter and antimatter meet, they annihilate and convert mass into energy with unmatched efficiency. In principle, a tiny amount of antimatter could release a huge amount of power. But producing antimatter is extraordinarily difficult. Particle accelerators can make it only in tiny quantities. Storing it is worse because antimatter cannot touch ordinary matter. It would need to be held in magnetic fields with near-perfect reliability. A failure would release energy violently and instantly. Then there are sails. A light sail uses photons, tiny packets of light, to push a reflective surface. Sunlight can do this gently, and a powerful laser could do it much more aggressively. The breakthrough Starshot idea imagines tiny gram-scale probes pushed by ground-based lasers to a significant fraction of light speed. A small chip could be accelerated this way. A huge crewed vessel could not, at least with anything close to present technology. The laser array would need staggering power, precision, and stability. Every option runs into the same cruel trade-off. A fast probe can be tiny, but fragile. A human ship can be protected, but massive. Add shielding, and the engine must push more mass. Add water, farms, spare parts, and medical systems, and the mass rises again. Add artificial gravity, radiation shelters, and enough room for generations to live, and the spacecraft becomes less like a probe and more like a city that must be accelerated through space. So the propulsion problem does not stay isolated. Even if humanity found a way to push such a ship to the required speed, that victory would create a new danger. The faster the ship moved, the less empty space would feel. Hydrogen atoms, dust grains, and tiny fragments drifting between the stars would begin to strike the spacecraft with terrifying force. At low speeds, interstellar space feels almost harmless. Voyager 1 can drift through it for tens of thousands of years because the space between stars is extraordinarily thin. In the local interstellar medium, the region our solar system is moving through now, there may be only a fraction of one particle in each cubic centimeter of space. Most of those particles are hydrogen atoms, with smaller amounts of helium, charged particles, dust grains, and traces of heavier elements made inside older generations of stars. For comparison, 1 cubic centimeter of air at sea level contains roughly 25 billion molecules. Interstellar space is emptier than anything humans experience on Earth. But emptiness changes when speed rises. At Voyager's speed, about 17 kilometers per second, an individual hydrogen atom striking the spacecraft has very little energy. The spacecraft can pass through this thin gas for ages, collecting tiny impacts across its surface. They may slowly weather exposed materials over immense time, but they do not instantly destroy the machine. At 10% of light speed, the same hydrogen atoms become a different problem. 10% of light speed is about 30,000 kilometers per second. At that speed, every hydrogen atom hitting the front of the spacecraft would arrive with millions of electron volts of energy. An electron volt is a tiny unit of energy used in atomic physics, but millions of them packed into individual particles is enough to damage materials atom by atom. The ship would no longer move through empty space. It would move through an invisible stream of high-energy impacts. A single hydrogen atom is tiny, but a large spacecraft would hit countless atoms every second. If the front of the ship had a cross-section of hundreds or thousands of square meters, the number of impacts would become enormous. Each impact would add a small amount of heat, radiation, and material damage. Over years or centuries, those small impacts would matter. Dust is worse. Interstellar dust grains are usually microscopic. Many are made from silicates, carbon compounds, or icy material. They are produced by dying stars, supernova explosions, and the slow chemical processes that happen in cold clouds between stars. A dust grain may be smaller than a speck of smoke, almost weightless by everyday standards. At a significant fraction of light speed, that speck becomes dangerous. Kinetic energy grows with the square of speed. Double the speed, and the impact energy becomes 4 times larger. increase the speed by 1,000, and the energy becomes 1,000,000 times larger. This is why a tiny object can become a serious threat when relative velocity is extreme. A dust grain with the mass of a few micrograms could strike like a small explosive charge. A larger grain, closer to the mass of fine sand, could punch a crater, vaporize material, and send a spray of hot plasma through the impact area. A pebble-sized object, rare but possible in space, could damage or destroy an unprotected spacecraft. The ship would need a forward shield. That shield might be a thick slab of material placed ahead of the main habitat. It might use layers with empty gaps between them, so incoming particles break apart before reaching the pressure hull. This kind of layered protection is similar in principle to Whipple shielding, used on spacecraft to protect against micrometeoroids. A thin outer layer shatters the incoming particle, and a deeper layer catches the spread-out debris. But an interstellar escape ship would need something far more serious. It might carry a massive block of ice at the front, because water is useful for absorbing radiation and can also serve as stored life support material. It might use magnetic fields to deflect charged particles, though neutral dust grains would pass through magnetic fields unaffected. It might send small detectors or sacrificial shields far ahead of the main ship, giving the vessel a little warning before it enters a denser patch of material. Every solution adds mass. A shield thick enough to protect a city-sized spacecraft would be heavy. More shielding means more material to accelerate. More material means more energy. More energy means larger engines, more fuel, larger power systems, and more heat to manage. So the protection needed for speed makes speed harder to reach. This is the trap hidden inside the journey. To escape the Milky Way quickly enough for the mission to have meaning, the spacecraft has to move incredibly fast. But the faster it moves, the more dangerous the galaxy becomes. Empty space turns into weather. Dust becomes ammunition. Hydrogen becomes radiation. The forward hull becomes one of the most important structures ever built. And once the ship carries enough protection to survive, it can no longer be a small craft with a few passengers. It has to become something much larger. A spacecraft built to escape the Milky Way could never be only an engine with a cabin attached. For a robotic probe, the problem is simpler. A small machine can carry cameras, antennas, power systems, navigation instruments, and protective shielding. It can go silent and still complete part of its purpose. It does not need food. It does not need sleep. It does not panic when Earth disappears behind it. A human crew changes everything. People need air with the right balance of oxygen and carbon dioxide. They need water every day. They need food with proteins, fats, carbohydrates, minerals, and vitamins. They need temperature control, waste removal, light cycles, exercise, medical care, and enough personal space to stay functional over long periods of confinement. On the International Space Station, astronauts already live inside a partial closed-loop system. Water from urine, sweat, and cabin humidity is collected, filtered, and reused. Carbon dioxide is removed from the air. Oxygen can be generated by splitting water molecules using electricity. But the station is still supported by Earth. Cargo spacecraft bring food, equipment, experiments, clothing, replacement parts, and emergency supplies. A galactic escape ship would have no cargo deliveries. Everything would need to be recycled, repaired, grown, stored, or manufactured on board. Water would have to move through the ship again and again, passing through filters, chemical processes, and microbial treatment systems. A single person can use several liters of water per day just for drinking and food preparation, and far more if washing, agriculture, and equipment cooling are included. Over decades or centuries, even a tiny loss rate becomes dangerous. Air would need the same careful management. Humans inhale oxygen and exhale carbon dioxide. Plants can reverse part of that cycle by using light to turn carbon dioxide and water into sugars, releasing oxygen in the process. But a stable biological system is hard to control. Crops can fail. Fungi can spread. Bacteria can contaminate water tanks. Insects, if used for pollination or protein, can escape their intended habitats. Food production would likely involve hydroponics or aeroponics. In hydroponics, plants grow with roots in nutrient-rich water. In aeroponics, roots hang in air and are misted with nutrients. These systems save soil and can produce food efficiently, but they require pumps, sensors, lights, fertilizers, and constant monitoring. Wheat, potatoes, soybeans, leafy greens, algae, and perhaps fish tanks could all become part of the ship's food web. The ship would also need artificial gravity. Long exposure to weightlessness causes muscle loss, bone thinning, fluid shifts, balance problems, and changes in vision. Astronauts on the International Space Station exercise for about 2 hours a day to slow these effects, and their missions usually last months, not lifetimes. A multi-generational ship would need a rotating section, using spin to create an outward force that feels like gravity along the inner wall. That means the habitat might be shaped like a wheel, a cylinder, or connected rotating modules. The larger the radius, the slower it can spin while still producing useful gravity. A small spinning room would make people dizzy because their heads and feet would move at noticeably different speeds. A large rotating habitat, perhaps hundreds of meters across, would feel much more natural. Then come the repair systems. A ship like this would need machine shops, 3-dimensional printers, metalworking tools, electronics labs, spare circuit boards, pumps, valves, seals, bearings, medical scanners, surgical tools, and storage for raw materials. A broken water pump could become as serious as an engine failure. A failed crop chamber could become a food crisis. A damaged radiator could threaten the ship's ability to shed heat into space. Power would have to run continuously. Nuclear reactors are the most realistic option for a large deep space habitat, because sunlight fades with distance from the sun and becomes useless long before the ship reaches even the nearest stars. Reactors would provide electricity for lights, computers, pumps, heating, cooling, manufacturing, communication, and propulsion support. And people would need more than survival. They would need schools, quiet rooms, gathering areas, exercise spaces, rituals, entertainment, privacy, and some version of normal life. A vessel meant to last across generations would need to feel less like a mission capsule and more like a small town sealed inside metal. At that point, the spacecraft stops being only a machine. It becomes a moving settlement. And a settlement has problems no engine can solve by itself. The first of those problems would begin before the spacecraft ever reached deep space. It would begin on Earth. At the moment, the first crew understood that launch was also farewell. A mission to escape the Milky Way would have no normal return plan. Even a mission to the nearest star would already stretch across decades with any technology close to what we can imagine. A mission aimed at leaving the galaxy would reach far beyond one human lifetime. The first people aboard would know that Earth was a place they were leaving permanently. That changes the meaning of launch. For astronauts traveling to the International Space Station, Earth remains close. The station orbits about 400 kilometers above the surface. A radio message can travel back and forth almost instantly. A return capsule can bring the crew home in hours. Even on the Moon, about 384,000 kilometers away, Earth hangs large in the sky, blue and bright, close enough for real-time conversation with only a short delay. A galactic escape ship would be different from the first day. At first, Earth would still look familiar through a rear-facing camera, a blue and white sphere with clouds moving over oceans, deserts, forests, and city lights. The crew could still receive messages from family. They could still watch recordings of rainstorms, streets, birthdays, crowded kitchens, birds moving through trees, waves breaking on shorelines. But none of those things would be reachable. They would have left open air behind. Real wind. Natural sunlight filtered through an atmosphere. The smell of soil after rain. The sound of leaves. The feeling of standing under a sky that is not made of metal, glass, radiation shielding, and life support machinery. Inside the ship, every breath would be manufactured. Oxygen would come from machines, plants, or stored reserves. Water would be filtered from yesterday's water. Food would grow under lamps. Day and night would be scheduled by clocks and lighting panels. Weather would be replaced by airflow from vents. Seasons would become something taught in lessons, marked on calendars, or preserved in recordings. And still, the emotional cost would not wait for the galaxy's edge. It would begin close to home. The first crew might pass the Moon in a few days. Mars's orbit in months. Jupiter after years, depending on the trajectory. They might watch the sun shrink from a warm disk into an intense white point. They might cross the outer planetary region, pass beyond Neptune's distance, and eventually move into the long darkness beyond the major planets. Every stage would make Earth less like a home they could return to, and more like an origin point. Communication would fade in a different way. Radio waves travel at the speed of light, so the delay grows with distance. Near Mars, a message can take several minutes to more than 20 minutes one way. Near Neptune, it can take about 4 hours. At 1 light year, a message takes 1 year. At 10 light years, 10 years. At first, the crew could still receive birthday greetings, news, instructions, songs, and recorded conversations from people they knew. Later, those messages would arrive late enough to feel out of season. A child born on Earth might be grown by the time a reply returned. A parent's voice might arrive years after the moment it was recorded. News would turn into history before it reached the ship. The crew would keep moving. Earth would keep changing. Cities would grow, governments would fall. Languages would shift. Families would age, and new generations would be born under the same sky the crew had left behind. the first generation aboard the ship would carry direct memory of Earth. They would remember gravity that came from a planet, oceans with real tides, clouds with no ceiling behind them, and horizons that did not curve into walls. They would become the living archive of what home felt like. But memory has a limit. As the years passed, the mission would belong less to the people who chose it, and more to the people who came after them. And those people would inherit a journey they never volunteered to begin. A child born aboard the escape ship would enter a universe no human child has ever known. Their first ceiling would be metal, insulation, wiring, and soft interior panels. Their first sky might be an observation window looking out into black space. Their first sunrise would come from programmed lights brightening inside a habitat ring. Their first weather would be the quiet movement of filtered air through vents. Earth would be real to them, but distant in the way ancient history is distant. They would learn about oceans through videos. They would see forests in archived recordings, with trunks, branches, leaves, insects, birds, and sunlight moving through canopies. They would study rain as a water cycle in a planet's atmosphere, where evaporation lifts water vapor into clouds and falling drops return it to rivers, lakes, and soil. They would know snow as frozen water crystals, beaches as places where land meets sea, and mountains as rock pushed upward by tectonic plates over millions of years. But they would never have stood in those places. Their normal world would be corridors, compartments, hatchways, pressure doors, hydroponic farms, exercise rooms, medical bays, storage modules, and rotating habitats. If the ship used spin gravity, they might grow up walking along the inner surface of a giant wheel or cylinder, with the floor always curving gently away in the distance. The force they felt under their feet would come from rotation, not from a planet pulling them downward. To them, that would feel ordinary. They would know that air is something maintained. They would understand, probably from childhood, that oxygen levels, carbon dioxide levels, humidity, temperature, and microbial contamination have to be monitored. A warning light in a life support system would carry the kind of seriousness that a storm warning carries on Earth. They would know that water is never simply used and forgotten. Water would be collected from sinks, showers, humidity, urine, plant systems, and industrial processes, then purified and returned to storage. A glass of water might contain molecules that had passed through the same ship thousands of times. This would not feel strange to them. It would feel responsible, practical, and normal. Food would also shape their world. They might help tend lettuce, potatoes, beans, algae tanks, dwarf wheat, or fruiting plants grown under red and blue agricultural lights. They might learn which crops provide calories, which provide vitamins, and which help keep the crew psychologically healthy, because fresh food matters in a closed environment. A ripe tomato might feel precious. A crop disease might feel frightening. A failed harvest would be a community emergency. Their education would have to be intense. A child on Earth can grow up surrounded by millions of adults, thousands of professions, and enormous institutions. A child on the ship would grow up inside one fragile system. They would need reading, mathematics, biology, physics, history, medicine, engineering, agriculture, and maintenance. They would need to understand why pumps fail, why seals leak, why metal fatigues, why radiation damages cells, and why a rotating habitat must stay balanced. The ship would have to teach its children how to keep the ship alive. That creates a strange kind of childhood. They would still play, form friendships, ask questions, get bored, laugh, argue, and dream. But beneath everything would be mission inheritance. Their home would also be a machine. Their school would also be survival training. Their family history would also be a launch decision made before they existed. Their identity would be difficult to define. Were they citizens of Earth, even if they had never touched it? Were they citizens of the ship? Were they travelers, colonists, exiles, or the first members of a new branch of humanity? Their ancestors would have chosen the journey. They would be born inside its consequences. And the destination would remain strange. If the mission aimed to escape the Milky Way, the children aboard might never see that final moment. Their grandchildren might not see it either. Generations could live and die while the galaxy still surrounded them. The purpose of the mission would have to survive through people who inherited the task, maintained the systems, and passed the story forward. That means the ship would need more than engines and air. It would need culture strong enough to hold people together, education strong enough to preserve knowledge, law strong enough to manage conflict, and a shared purpose strong enough to last longer than memory. A culture aboard the escape ship would have to do something very difficult. It would have to keep people human, while also keeping the machine alive. On Earth, civilization is spread across continents. If one hospital closes, there are others. If one power station fails, electricity can be rerouted. If one farm has a bad harvest, food can arrive by truck, ship, rail, or aircraft from somewhere else. Earth has redundancy built into its size. A spacecraft would have almost none of that comfort. Its farms, hospitals, classrooms, workshops, water systems, power systems, and living spaces would all be sealed inside one moving structure. Every resource would be counted. Every repair would matter. Every decision would carry physical consequences. Leadership would have to be clear but flexible. A ship might begin with a captain and mission command structure, similar to a naval vessel or spacecraft crew. But across generations, that command structure would become a government. People born aboard would need representation, rights, responsibilities, and a way to challenge decisions without breaking the community apart. There would need to be laws. Some laws would be familiar. Rules against theft, assault, sabotage, and reckless behavior. Others would be unique to a closed spacecraft. How much water can one person use? Who gets access to private rooms? Who decides crop allocation after a harvest failure? Who chooses which machine parts are repaired first when two systems need the same limited material? On Earth, a political argument can be noisy and still remain survivable. On a ship, a political argument over oxygen production, reactor maintenance, or food storage could threaten everyone. Healthcare would also become part of the ship's foundation. The community would need doctors, nurses, surgeons, dentists, pharmacists, genetic counselors, psychologists, physical therapists, and medical technicians. They would need imaging equipment, surgical tools, sterilization systems, medicines, vaccines, and the ability to manufacture some drugs as old supplies expired. Even common problems would become serious in isolation. A broken bone, infected tooth, premature birth, crop-related food deficiency, or failed air filter could not be handled by calling for outside help. The ship would have to be its own clinic, hospital, pharmacy, and public health department. Education would be just as important as medicine. The ship could survive one generation of skilled engineers. It could fail if their knowledge disappeared. Children would need to learn how the habitat rotates, how water recycling works, how reactors produce heat, how radiators release that heat into space, how carbon dioxide scrubbers keep the air breathable, and how hydroponic nutrients move through plant roots. They would also need history, language, art, music, ethics, and memory. A society that teaches only maintenance might keep the ship running, while slowly losing its reason for existing. A society that teaches only purpose and stories might forget how to repair the pumps. The balance would be delicate. Small failures could become social crises. Imagine a pump breaking in one hydroponic chamber, reducing the lettuce and soybean crop by 10% for several months. The technical problem is a pump. The social problem is food distribution. Do children receive the same portions as adults? Do workers doing heavy physical repair receive more calories? Do elders receive less? Who decides? Or imagine a radiation storm damaging electronics in a storage module. Spare parts are limited. One team needs components for medical scanners. Another needs them for navigation sensors. Both are important. Neither can simply order replacements. Every shortage becomes a test of trust. That trust would have to be maintained through rituals, public records, transparent decisions, and shared responsibility. The ship might hold regular assemblies. It might preserve written laws and technical manuals in multiple formats. It might train apprentices under older specialists, the way craft knowledge was passed down before modern industry. Because over time, Earth would become less useful as a guide. At first, mission control might send instructions, software updates, advice, and encouragement. Later, delays would stretch into years, then centuries, then longer. Earth could still speak, but it could no longer manage daily life aboard the ship. The people inside would have to become fully responsible for themselves. And as the ship moved farther into the galaxy, Earth would become less like a command center and more like a distant ancestor. At first, Earth could still feel present. A message sent from the ship near the Moon would take a little over 1 second to reach home. Near Mars, the delay could be anywhere from a few minutes to more than 20 minutes, depending on where Earth and Mars were in their orbits. Near Neptune, radio signals would need about 4 hours to cross the distance. That would already feel slow, but it would still be communication. Mission controllers could send instructions. Families could send recordings. Scientists could share discoveries. Children aboard the ship could receive lessons from Earth, music from Earth, holidays from Earth, and images of places they would never walk through. But as the ship moved farther away, light itself would become the limit. Radio waves, laser signals, and every other ordinary form of electromagnetic communication travel at the speed of light. That sounds fast, because light can circle Earth more than 7 times in 1 second. It crosses the distance from Earth to the Moon in about 1.3 seconds. It reaches the Sun in about 8 minutes and 20 seconds. But across the galaxy, light becomes slow. At 1 light year away, a message takes 1 year to arrive. At 10 light years, it takes 10 years. At 100 light years, it takes a century. At 1,000 light years, a message from Earth would need 1,000 years to reach the ship. A reply would need another 1,000 years to return. That turns a single exchange into a 2,000-year loop. Someone on Earth could send a question, and the answer would return to a civilization that might speak different languages, live under different governments, use different technologies, and remember the original sender only as a historical figure. A warning about a system failure might arrive long after the system had already been repaired, replaced, abandoned, or allowed to fail. A message of comfort might reach people whose ancestors were the ones who needed it. This changes the meaning of news. At first, Earth could send reports about current events, new spacecraft, new discoveries, new cities, new problems, new leaders. Later, those reports would become history before they arrived. A message describing a war, election, disaster, invention, or scientific breakthrough would reach the ship centuries after it happened. By the time anyone aboard heard it, the consequences would already be buried deep in Earth's past. The ship would experience Earth through delayed layers. A transmission from the year 3000 might arrive when the ship's calendar reads 4000, depending on distance. A reply sent with care and ceremony might return when the original Earth culture had changed beyond recognition. Eventually, the archive of incoming messages would feel less like a conversation and more like a museum being delivered slowly through space. The people aboard would still listen. They might gather in common rooms to hear ancient broadcasts. They might preserve recordings of Earth's oceans, forests, languages, ceremonies, street sounds, thunderstorms, and animal calls. They might study old messages the way historians study clay tablets, ship logs, letters, or radio recordings from the early 20th century. Earth would keep speaking, but its voice would arrive from the past. The technical side would be difficult as well. A signal spreads out as it travels, growing weaker with distance. To communicate across hundreds or thousands of light years, the ship and Earth would need powerful transmitters, enormous receiving dishes, or tightly focused laser communication. The pointing would have to be precise. A tiny aiming error across light years could miss the receiver completely. Even if the signal arrived, the meaning would need protection. Languages change, file formats change, symbols change. Measurements, calendars, political borders, and cultural references change. The ship would need translation systems, preserved dictionaries, redundant archives, and stable ways to decode messages sent by people who lived centuries earlier. Eventually, Earth could no longer guide the ship in any practical sense. It could send memory. It could send history. It could send blessings, discoveries, and warnings from ages already gone. But it could no longer command, rescue, correct, or comfort in time. The relationship would become symbolic. Earth would remain the origin, the first home, the place in the old recordings where rain fell from an open sky. But the ship would have to live by its own decisions, carrying Earth as memory while moving deeper into the galaxy on its own. The ship's first true galactic landscape would be the region humans already live inside. Our solar system sits in a smaller structure of the Milky Way, called the Orion Arm, or Orion Spur. It is not one of the galaxy's largest spiral arms. It is a smaller bridge of stars and gas located between two larger arms. The Sagittarius arm closer toward the galactic center, and the Perseus arm farther outward. From Earth, this local region feels like the whole sky. It contains the stars of Orion, Taurus, Gemini, Canis Major, Cassiopeia, Cygnus, and countless others that humans grouped into constellations long before we understood what they were. But those patterns are only line-of-sight arrangements from Earth. The stars in a constellation are usually scattered across very different distances. Orion is a good example. Betelgeuse, the red supergiant marking Orion's shoulder, is hundreds of light years away. Rigel, the blue-white star at Orion's foot, is also hundreds of light years away, but at a different distance and moving on its own path. The three stars of Orion's belt look close together in Earth's sky, but they are separate massive stars spread across deep space. The shape exists because of where we are standing. As the escape ship moved far enough from the solar system, those shapes would slowly break. At first, the constellations would still look familiar. The ship might travel for centuries or thousands of years, and the sky would change only slightly to human eyes. But across tens of thousands of years, and especially across light years of distance, the patterns would stretch, tilt, and dissolve. Stars that once formed a hunter, a bull, a swan, or a queen would drift into new positions. Some would grow brighter from the ship's perspective. Others would fade. The night sky would become unrecognizable. The ship would pass through neighborhoods dominated by red dwarfs, the smallest and most common stars in the galaxy. Proxima Centauri is one of them. So is Barnard's star, about 6 light years from Earth, a dim red dwarf moving quickly across our sky. Red dwarfs burn slowly and faintly. Many can last for hundreds of billions or even trillions of years, far longer than the current age of the universe. There would also be sun-like stars, yellow and orange stars with lifetimes measured in billions of years. Some might have planets. Some might have asteroid belts, icy outer regions, or giant planets in wide orbits. There would be white dwarfs too, the dense cooling cores left behind after stars like the Sun exhaust their fuel and shed their outer layers. Sirius B, the companion to the bright star Sirius, is one nearby example of a white dwarf, with about the mass of the Sun compressed into an object roughly the size of Earth. The ship might also pass near darker remnants. Neutron stars, formed from the collapsed cores of massive stars, can pack more mass than the Sun into a sphere only about 20 kilometers wide. Black holes left behind by dead stars may drift through the galaxy without glowing, unless they are feeding on gas or passing near another star. Most would be difficult to see directly. Their presence would be known by gravity, radiation, or the motion of nearby objects. Between the stars, the ship would cross regions of thin interstellar gas and dust. Some of this material sits inside the local bubble. a large, low-density cavity around the Sun, likely carved by ancient supernova explosions millions of years ago. Other regions are denser and colder, including molecular clouds, where hydrogen molecules gather and new stars can form. These clouds can look dark against the background of the Milky Way because dust inside them blocks visible light. So leaving the local region would not mean flying through perfect emptiness. It would mean moving through a slow, uneven galactic environment. Red stars, old stellar corpses, thin gas, dark clouds, magnetic fields, drifting dust, and the ruins of stars that died long before humans existed. And all of it would be moving too. The ship would leave behind the sky humans recognize, but the galaxy around it would keep rotating, shifting, and carrying every star along its own long orbit. From Earth, the Milky Way can look like a fixed map. It is easy to imagine a spacecraft choosing a route, pointing itself between known stars, and following that path for thousands of years. But the galaxy is alive with motion. Every star is moving. Every gas cloud is drifting. Every cluster is orbiting. Even the ship itself is being pulled by the combined gravity of the galaxy as it travels. The Sun orbits the galactic center at about 220 kilometers per second. Nearby stars move at their own speeds, some close to the Sun's motion, others cutting through the local neighborhood at sharper angles. Barnard's star is one of the clearest examples. It sits about 6 light-years from Earth and has the fastest known apparent motion of any star in our sky, shifting by about 10 arseconds each year. That sounds tiny, but over a human lifetime, its movement can be measured against the background stars. Over thousands of years, its position changes dramatically. Other stars move more slowly from our point of view, but they are still traveling through the galaxy. Sirius, Alpha Centauri, Procyon, Vega, and countless red dwarfs are all following their own paths. Some are approaching our region. Some are moving away. Some will pass closer to the Sun in the far future, while others that look bright tonight will slowly become more distant. A spacecraft trying to escape the Milky Way would have to navigate through that moving system. A map made at launch would begin aging immediately. A star's position is already slightly out of date by the time its light reaches us. Alpha Centauri is more than 4 light-years away, so we see it where it was more than 4 years ago. A star 1,000 light-years away is seen as it was 1,000 years in the past. For a short mission, those delays can be handled. For a journey across thousands or millions of years, they become part of the mission itself. The ship would need to calculate where stars are going, rather than only where they appear to be. It would need to account for proper motion, which is a star's movement across the sky, and radial velocity, which is its motion toward or away from the observer. It would also need to account for the galaxy's gravity slowly bending its own path. This is closer to sailing through a moving ocean than driving across a road. The ship would not be passing fixed landmarks. It would be moving through currents of stars, gas, and gravity. A molecular cloud that appears far ahead at launch could shift. A nearby red dwarf could cross the ship's future path after tens of thousands of years. A dense region of dust could become more important as the vessel's route carries it toward a different part of the Orion Arm. Tiny errors would grow. If a spacecraft's course were off by only a fraction of a degree, that error would be small near the start. Across 1 light year, it could become billions of kilometers. Across 1,000 light years, it could become a mist so large that the original target region disappears from the useful path entirely. Navigation would require constant correction. The ship might use pulsars as cosmic lighthouses. Pulsars are spinning neutron stars that send beams of radiation into space, and some pulse with extremely regular timing. By comparing the arrival times of pulses from several known pulsars, a spacecraft could estimate its position in the galaxy. It might also use star trackers, gravitational maps, and long-range telescopes to update the route as the sky changed. But every correction costs something. A course adjustment uses fuel, power, reaction mass, or stored energy. A small correction made early can prevent a huge miss later. A correction delayed too long can become expensive or impossible. Over centuries, navigation becomes a quiet battle against accumulated error. The galaxy slowly stops feeling like a chart. It becomes an environment, a moving, rotating, shifting system of stars and clouds, where the safest path has to be found again and again. As the ship moved deeper through the Milky Way, the emptiness around it would keep changing. Interstellar space is thin, but it is uneven. Some regions contain only a few atoms scattered through each cubic centimeter. Other regions are thicker, colder, darker, and richer in gas and dust. The ship would pass through a galaxy that looks calm from far away, but up close is filled with quiet structure. Most of the material between stars is hydrogen. Hydrogen is the simplest element in the universe. One proton with one electron. Some of it floats as single atoms. Some gathers into hydrogen molecules inside cold molecular clouds. These clouds can reach temperatures only 10 or 20 degrees above absolute zero, cold enough that atoms move slowly and dust blocks visible starlight. Inside those clouds, stars are born. Gravity pulls gas inward. Denser pockets collapse. As the material falls together, it heats up, forms a rotating disk, and eventually creates a new star at the center. The Orion Nebula, about 1,300 light-years from Earth, is one of the most famous nearby star-forming regions. Through telescopes, it looks like a glowing cloud beneath Orion's belt. But physically, it is a vast nursery of gas, dust, and newborn stars. An escape ship passing near a region like that would encounter more particles, more dust, stronger local radiation, and more complex magnetic fields. Magnetic fields matter because much of interstellar gas is plasma. Plasma is gas where some atoms have been stripped of electrons, leaving charged particles behind. Charged particles respond to magnetic fields. They spiral along field lines, gather in waves, and help shape the movement of gas across huge regions of space. The ship would also cross the remains of dead stars. When a massive star runs out of fuel, its core can collapse and trigger a supernova. The explosion throws heavy elements into space: oxygen, silicon, iron, nickel, calcium, and many of the ingredients that later become planets and living bodies. These expanding shells are called supernova remnants. The Crab Nebula, created by a supernova observed from Earth in the year 1054, is one example. At its center is a pulsar, a rapidly spinning neutron star sending beams of radiation into space. A ship would try to avoid active remnants and high radiation regions. Cosmic rays would be a constant concern. These are high-energy particles, often protons or atomic nuclei, moving at close to the speed of light. Some are accelerated by supernova shock waves. Some come from more extreme environments, such as pulsars or black holes, feeding on nearby matter. On Earth, the atmosphere and magnetic field shield life from much of this radiation. In deep space, the ship would need its own protection. Water, fuel, and thick shielding could help absorb some radiation. Magnetic fields might deflect charged particles, but the protection would never be perfect. Over decades and centuries, radiation damages electronics, weakens materials, and can break chemical bonds inside living cells. Then there are rogue planets. A rogue planet is a planet that no longer orbits a star. It may have been thrown out of its original system by gravitational encounters with giant planets or passing stars. The Milky Way may contain billions of them, drifting in darkness between star systems. Most would be nearly impossible to see from far away because they produce little light of their own. The odds of hitting one would be tiny because the galaxy is so vast. But navigation would still treat them as possible hazards. A rogue gas giant, a frozen rocky world, or a loose cloud of debris could quietly occupy a path that looks empty from light years away. The ship would need long-range detection, careful route planning, and the ability to adjust course before a distant object became a crisis. So the journey would pass through emptiness, but not simplicity. Thin gas, cold clouds, dust grains, magnetic fields, radiation, dead stars, hidden planets. Most of the time, the ship would see only blackness and distant points of light. Yet over enough distance and enough time, even rare hazards become part of the landscape. Eventually, after ages of travel, the bright, crowded disk of the Milky Way would begin to thin around the ship. But the galaxy's visible stars are only the part we can see. For most of the journey, the ship would still be inside the bright part of the Milky Way. The galaxy's visible disk is the flat, star-filled structure we usually imagine when we picture the Milky Way from the outside. It contains most of the galaxy's stars, most of its gas, most of its dust, and the spiral arms where new stars are still forming. From far away, it would look like a glowing wheel, with dusty lanes wrapped around a brighter central region. That disk is enormous. It is about 100,000 light-years across, but only about 1,000 light-years thick in its thinner stellar regions. Near the center, the galaxy swells into a thicker bulge packed with older stars. Farther out, the disk becomes flatter and more spread out, with spiral arms tracing regions where gas clouds, young stars, and star-forming nebulae are more common. Earth is buried inside this disk. That is why the Milky Way appears from Earth as a pale band across the night sky. We are looking through the galaxy from within it, seeing the combined glow of countless distant stars mixed with dark clouds of dust that block visible light. The dark patches in the Milky Way are not empty holes. They are thick curtains of dust and gas between us and the stars behind them. As the escape ship moved far enough above or beyond the disk, that view would change. The Milky Way would stop surrounding the crew in every direction. The crowded star fields would begin to gather behind them. The glowing band that once stretched across the sky would widen, flatten, and slowly become a single structure. The ship would begin seeing the galaxy the way we see other galaxies through telescopes, as an object suspended in darkness. At first, the change would be subtle. The sky would still contain stars in every direction. The nearest stars would still appear as bright points. But over long distances, the density would begin to fall. There would be fewer nearby stars, fewer glowing clouds, fewer dark nebulae cutting across the view. The ship would move into a region where the Milky Way's disk was no longer the environment around it, but the landscape behind it. That would be one of the strangest visual milestones of the entire journey. For the first time, the crew could look back and see home as part of a galaxy-shaped glow. The sun would be lost inside it, too faint and too deeply embedded to stand out. Earth would be completely invisible. Every ocean, every mountain, every city, every recorded human life would be hidden inside one distant region of light. The galaxy would no longer feel like the sky. It would feel like a place they had left. From that vantage point, the spiral structure might become easier to understand. The central bulge would glow more warmly and densely, filled with older stars. Dust lanes would curve across the disk like dark rivers. Star-forming regions would shine with blue young stars and reddish clouds of hydrogen gas. Globular clusters, dense spherical groups of ancient stars, would hang around the galaxy like sparks around a fire. But this view would also create a false sense of escape. Leaving the bright disk does not mean leaving the Milky Way. The visible stars are only the part the eye can easily imagine. The galaxy's gravitational influence reaches much farther than its brightest light. Even beyond the main disk, the ship would still pass through the outer stellar halo, where old stars and globular clusters orbit on wide, tilted paths. Some of these halo stars are extremely ancient, formed more than 12 billion years ago when the Milky Way was still young. They contain fewer heavy elements than younger stars like the Sun, because they formed before many generations of supernovae had enriched the galaxy with iron, carbon, oxygen, and silicon. So even outside the disk, the ship would still be moving through the galaxy's history. Old stars, ancient clusters, faint streams from smaller galaxies the Milky Way tore apart long ago. And beyond all of that, something even larger would remain. The bright disk would thin behind the ship, but the invisible mass of the Milky Way would still reach farther. The farther the ship moved from the bright disk, the stranger the Milky Way would become. Behind it, the galaxy would look smaller and more complete. A glowing disk, a central bulge, spiral arms wrapped in dust, ancient star clusters scattered around it. From a distance, it might seem as if the ship had finally left the main body of the galaxy behind. But gravity would still be there. The Milky Way's visible matter is only part of its mass. The stars, gas, dust, nebulae, stellar remnants, and central black hole all contribute gravity, but they do not explain how the galaxy moves. Astronomers learned this by studying rotation curves, which show how fast stars and gas orbit at different distances from the galactic center. In a simple system, objects farther from the center should orbit more slowly. In our solar system, Mercury moves around the Sun at about 48 kilometers per second. while Neptune moves at only about 5.4 kilometers per second. The father planet moves slower because most of the mass is concentrated in the Sun. Galaxies behave differently. In the outer parts of spiral galaxies, stars often keep moving at high speeds instead of slowing down as much as visible matter predicts. This was one of the major clues studied by astronomers like Vera Rubin and Kent Ford in the 1970s. Their measurements help show that galaxies contain far more mass than we can see. That unseen mass is called dark matter. Dark matter does not shine like a star. It does not glow like hot gas. It does not form bright clouds, reflect starlight, or block light like dust. Telescopes cannot photograph it directly. Astronomers detect it through gravity, by watching how stars orbit, how gas moves, how satellite galaxies behave, and how light from distant objects bends as it passes through massive regions of space. Around the Milky Way, dark matter appears to form a vast halo. A halo is a roughly spherical region surrounding the galaxy. The bright disk of the Milky Way is flat, like a thin glowing plate, but the dark matter halo extends around it in every direction. It reaches far above the disk, far below it, and far beyond the visible spiral arms. The scale is enormous. The stellar disk of the Milky Way is about 100,000 light-years across. The dark matter halo may extend hundreds of thousands of light-years from the galactic center, possibly out toward the region where the Milky Way's influence begins blending with the gravity of nearby galaxies. The total mass of the Milky Way, including dark matter, is often estimated at around 1 trillion times the mass of the Sun, though measurements vary. That means a spacecraft could travel beyond the main star field and still remain inside the Milky Way's larger gravitational structure. The ship might look back and see the galaxy as a distant island of light, yet still be climbing through the invisible slope of its gravity. There would be fewer stars nearby, less gas, less dust, fewer glowing clouds. The environment would feel emptier, colder, and more open. But the ship would still belong to the Milky Way in the one way that matters for escape. Its path would still be shaped by the galaxy's mass. This makes the final stage feel different from the first. Early in the journey, the obstacles are visible and physical. Earth's gravity, the planets, the outer solar system, the star fields of the Orion Arm, dust clouds, radiation, stellar remnants. The dark matter halo is quieter. There is no wall to cross, no surface, no border painted across space. The ship would pass through it without seeing it, feeling only its effect through the slow curve of its trajectory. The final prison is invisible, and the only proof that it is there is the way it refuses to let motion become freedom. So the last part of galactic escape would feel almost unreal. The ship would be far beyond the familiar stars, beyond the bright disk, beyond the sky humans once named from Earth. And still, the Milky Way would be holding on. Only when the spacecraft had enough speed to stop curving back would the journey change into something else. Only then would it become truly unbound. At some immense distance, after crossing the bright disk, the outer halo, and the long invisible reach of dark matter, the ship would pass a threshold that no eye could see. There would be no gate, no flash of light, no clean boundary where the Milky Way ended. The change would be mathematical, but it would be real. The spacecraft's speed and direction would finally be enough that the galaxy could no longer curve its path back inward. It would still feel the Milky Way's gravity, because gravity fades with distance, but never simply switches off. Yet the pull would be too weak to reclaim it. The ship would have become gravitationally unbound. This is the same basic principle that separates orbit from escape. A spacecraft leaving Earth can pass above the atmosphere and still remain tied to the planet. It can circle Earth for years, like the International Space Station, because its sideways motion and Earth's gravity balance into an orbit. To escape, it must carry enough energy that its path stays open instead of closing back around the planet. The same idea applies on a galactic scale. A star can orbit the Milky Way for billions of years. The Sun has done this since it formed about 4.6 billion years ago, completing only around 20 galactic orbits in that entire time. A spacecraft moving through the galaxy can also follow a long curved path, pulled by the disk, the central bulge, and the dark matter halo. But an unbound object is different. Its path is no longer a loop. It is an open curve, stretching away into intergalactic space. Astronomers already know that some objects can be thrown out of galaxies. Hypervelocity stars are one example. These are stars moving so fast that some may eventually escape the Milky Way. The first confirmed examples were discovered in the early 2000s. One likely mechanism involves the supermassive black hole at the galactic center. If a binary star system passes too close to Sagittarius A star, one star can be captured while the other is flung outward at tremendous speed. The escaping star becomes a natural demonstration of galactic exile. It was born inside the Milky Way. Then gravity itself threw it away. A spacecraft would need to achieve something similar by design. It would need to carry enough energy, or gain enough through propulsion and carefully planned gravitational maneuvers, to stop belonging to the galaxy's orbiting population. It would become more like a hypervelocity traveler than a planet, probe, or ordinary star. The ship's instruments would confirm this slowly. Navigation systems would track the galaxy behind it. Star positions would shift. The pull of the Milky Way would keep weakening. Models of the ship's trajectory would show that its future path no longer returned through the halo, the disk, or the spiral arms. Over millions or billions of years, it would keep moving outward. That would be the moment of escape. Yet nothing inside the habitat might change. The air would still move through vents. Crops would still grow under artificial lights. Water would still pass through filters. Children would still study, sleep, argue, and eat. Engineers would still inspect seals, pumps, radiators, bearings, reactors, and guidance systems. The people aboard might mark the crossing with ceremony, but the ship itself would feel the same. That may be the strangest part. One of the greatest departures imaginable could happen quietly. A line in a navigation model. A change in a future path. A message written into the ship's archive saying that, from this point onward, the vessel is no longer a galactic object. It has become intergalactic. The Milky Way would still dominate the view behind them, but it would no longer own their future. The galaxy that formed the Sun, Earth, and every human body would now be a place they were moving away from forever. The victory would be real, but it would bring no harbor, no new world, and no nearby shore. Beyond the Milky Way, the ship would enter a deeper emptiness, where escape finally succeeds and the reward is distance itself. Beyond the Milky Way, the ship would enter a kind of space almost no human imagination is built to hold. Inside the galaxy, space is already empty by Earth standards. The distance between the Sun and the nearest star system is more than 4 light years. The space between stars contains only thin gas, dust, magnetic fields, radiation, and the occasional wandering object. It is emptier than the best vacuum chambers humans can build. Intergalactic space is emptier still. Between galaxies, there are no familiar star neighborhoods, no dense spiral arms, no glowing nebulae like the Orion Nebula, no rich fields of nearby red dwarfs, white dwarfs, and sun-like stars scattered around the ship. There may still be gas, dark matter, magnetic fields, cosmic rays, and faint materials stripped from galaxies during ancient gravitational encounters. But the density drops to a level that feels almost beyond comparison. A cubic meter of air on Earth contains about 25 trillion molecules. A cubic meter of interstellar space might contain only a few 100,000 particles, depending on the region. In the vast space between galaxies, the average density can be far lower again. Instead of moving through a sea of stars, the ship would be moving through the dim space between stellar islands. The nearest major galaxy to the Milky Way is Andromeda. Andromeda is about 2.5 million light years away. It is a huge spiral galaxy, larger in visible extent than the Milky Way, containing perhaps around 1 trillion stars. From Earth, under very dark skies, Andromeda appears as a faint smudge in the constellation Andromeda. It is the farthest object most people can see with the unaided eye. But from an escaped ship, Andromeda would still be impossibly far away. If the spacecraft had only just become unbound from the Milky Way, it would still be nowhere close to another galaxy. It would have solved the problem of leaving one cosmic island, only to discover that the next island is separated by an ocean, millions of light years wide. Even light needs 2.5 million years to cross from Andromeda to Earth. That means the light we see from Andromeda tonight began its journey before modern humans existed, before Homo sapiens, before cities, before language as we know it, before agriculture, before every recorded civilization. It began traveling when early human relatives were still living in Africa, shaping stone tools, walking through landscapes filled with animals now long gone. A spacecraft moving far slower than light would face a distance that makes even galactic escape feel small. At 10% of light speed, crossing 2.5 million light years would take 25 million years, without even counting acceleration, deceleration, course corrections, maintenance, or survival. At 1% of light speed, it would take 250 million years, longer than one full orbit of the Sun around the Milky Way. Andromeda is also moving toward the Milky Way. In about 4 billion years, the two galaxies are expected to begin merging, pulled together by gravity. Their stars will mostly pass between one another, because stars are so small compared with the distances between them. but the galaxies themselves will distort, stretch, and eventually blend into a larger structure. For the ship, that future would be almost meaningless on human time. The vessel would be traveling through darkness while galaxies changed on scales of hundreds of millions and billions of years. There might be smaller targets in intergalactic space. Dwarf galaxies orbit the Milky Way, including the large and small Magellanic Clouds, visible from Earth's southern hemisphere. There are also faint satellite galaxies, stellar streams, and isolated stars thrown out during gravitational encounters. But compared with the rich disk of the Milky Way, these would be rare islands scattered through immense dark volume. Escaping the galaxy would therefore create a strange victory. The ship would be free. Its path would no longer belong to the Milky Way. Its future would no longer curve back toward the spiral arms, the Orion Spur, the Sun, or Earth. The gravitational prison would finally be behind it. But freedom would look like emptiness. No nearby world, no waiting star, no welcoming shore. Only distance opening in every direction, with the Milky Way behind and the next great galaxy still millions of light years ahead. Escaping one impossible structure would reveal something larger and quieter. The space between galaxies is not a destination. It is the beginning of a deeper isolation. From far outside the galaxy, the Milky Way would finally become visible as a whole. The ship would no longer see it as a pale band across the sky, the way humans saw it from Earth for thousands of years. It would no longer be a crowded field of stars surrounding the crew in every direction. It would appear as a vast glowing island in the dark, a flattened spiral of starlight, dust, gas, and ancient structure. The central bulge would shine brightest, packed with old stars orbiting near the galactic center. Hidden inside that region would be Sagittarius A star, the supermassive black hole with about 4 million times the mass of the Sun. Around it, stars move at incredible speeds, some whipping through tight orbits that helped astronomers measure the black hole's mass in the first place. Stretching away from that center would be the spiral arms. They would look like curved lanes of stars and gas, wrapped around the galaxy in a slow pattern. Bright blue regions would mark places where young massive stars had formed recently. Reddish hydrogen clouds would show stellar nurseries, where ultraviolet light from newborn stars makes gas glow. Dark dust lanes would cut across the disk, blocking visible light from stars behind them. From that distance, the galaxy would look quiet, but inside that quiet light would be everything humanity ever knew. Earth would be there, completely invisible. A rocky planet about 12,700 kilometers wide, orbiting one ordinary yellow star in the Orion Spur. The moon would be there too, circling Earth every 27 days. Mars, Jupiter, Saturn, Uranus, Neptune, the asteroid belt, the Kuiper belt, and the distant icy bodies of the outer solar system would all be hidden inside the same tiny region of the same glow. Every human city would be inside it. Cairo, Beijing, Lagos, New York, Mumbai, London, Toronto, Mexico City, Tokyo, Sao Paulo, and every village, road, farm, harbor, airport, and quiet home would be buried in that distant light. Every ocean would be there. The Pacific, the Atlantic, the Indian Ocean, the Arctic, and the Southern Ocean. Every mountain range, every desert, every river system, every forest, every glacier, all of it would be too small to see. The ship could look back with telescopes, but even the sun would be hard to separate from the crowd of stars around it. It would be one point among hundreds of billions. Earth would vanish completely in the glare and distance, smaller than a dust mote beside a lamp. The familiar constellations would also be gone. Orion, Cassiopeia, the Big Dipper, Scorpius, Cygnus, and Taurus were never permanent structures. They were patterns created by Earth's position inside the galaxy. From outside, those shapes would dissolve. Betelgeuse, Rigel, Sirius, Vega, Polaris, and Alpha Centauri would all belong to the same great disk. But their old arrangements would no longer frame the sky. Home would stop being a place with directions. It would become a region inside a galaxy. That may be the deepest emotional change of the journey. The crew would still have maps, archives, recordings, and historical coordinates. They could still say where Earth was, mathematically. They could still point toward the Milky Way and say the home world was inside it. But pointing would feel different from returning. The galaxy would contain the entire story of life as humans understood it. The first cells in ancient oceans, the rise of oxygen, the age of dinosaurs, the first mammals, the first humans walking under African skies, the first fires, tools, languages, farms, temples, ships, telescopes, rockets, satellites, and spacecraft. Every memory would be inside one distant spiral. The ship would have escaped, and the cost of that escape would finally be visible. The Milky Way would shine behind them as the most beautiful thing they had ever left, and the most unreachable thing they had ever known, which leaves the journey with a strange weight. What kind of species chooses to go that far? A journey like this would be terrifying because it asks for almost everything a species can give: energy, time, knowledge, patience, generations, the willingness to leave behind the galaxy that made every living thing we know. And yet, if humanity ever became capable of attempting it, there would still be reasons people might go. One reason is survival. Earth has already lived through catastrophes large enough to reshape life. About 66 million years ago, an asteroid roughly 10 kilometers wide struck near what is now the Yucatan Peninsula in Mexico. The Chicxulub impact helped end the age of non-avian dinosaurs and changed the direction of life on Earth. Long before that, mass extinctions caused by climate shifts, volcanic eruptions, ocean chemistry changes, and falling oxygen levels erased huge portions of living species. A civilization that thinks in millions or billions of years eventually has to face this reality. Planets are fragile. Stars change. Galaxies change. The sun is stable now, but over the next several billion years, it will brighten, changing Earth's climate long before it becomes a red giant. The Milky Way itself is moving toward Andromeda, and in several billion years, the two galaxies are expected to merge into a larger system. A species that spreads beyond one world is harder to erase. A species that spreads beyond one star is harder still. And a species that can eventually cross beyond one galaxy has turned survival into something cosmic. Curiosity would be another reason. Human beings have always crossed boundaries before they fully understood what was beyond them. Ancient Polynesian navigators crossed the Pacific using stars, swells, winds, birds, and cloud patterns, reaching islands separated by thousands of kilometers of ocean. Sailors crossed the Atlantic with wooden ships, magnetic compasses, and incomplete maps. Explorers crossed deserts, ice sheets, mountain ranges, and continents long before those landscapes were safe or fully known. The same instinct carried upward. In 1903, the Wright brothers flew at Kitty Hawk for only 12 seconds on their first successful powered flight. In 1957, Sputnik 1 became the first artificial satellite. In 1961, Yuri Gagarin became the first human to orbit Earth. In 1969, Apollo 11 landed on the Moon. In 1977, Voyager 1 and Voyager 2 launched toward the outer planets and eventually continued into interstellar space. Each step once seemed like a boundary. Then it became a place. The atmosphere became a place we could cross. Orbit became a place we could work. The Moon became a place where boot prints could remain in dust. Mars became a world photographed by orbiters and explored by rovers. Jupiter, Saturn, Uranus, and Neptune became real worlds with storms, rings, moons, oceans, volcanoes, and magnetic fields. Escaping the Milky Way would be the largest version of that same pattern. It would carry scientific ambition beyond the scale of any previous mission. A ship outside the galaxy could study the Milky Way as a complete object. It could measure the outer halo directly, map faint streams of ancient stars, sample intergalactic gas, and look back at our galaxy without being buried inside its dust and starlight. It might also carry life. Seeds, microbes, human DNA, animal embryos, digital archives, languages, music, mathematics, images of Earth, records of oceans, forests, storms, cities, and faces. A galactic escape mission might become an ark, a library, a laboratory, and a message all at once. The cost would be almost unimaginable. The people who began it might never see its greatest milestone. Their descendants might live and die inside the mission. Earth's voice would fade into history. The Milky Way would slowly become a distant island of light behind them. And still, some would go. Because the terrifying part of this journey is also the human part. We look at boundaries and eventually wonder what lies beyond them. We learn the danger, calculate the distance, build the tools, tell the story, and then someone takes the first step. Escaping the Milky Way would be frightening, lonely, and almost impossibly difficult. It would also be one of the clearest expressions of what humanity has always done when faced with a horizon. So by the end of this journey, the path behind the ship would tell a story almost too large to hold. It would begin on Earth, a rocky planet about 12,700 kilometers wide, wrapped in a thin atmosphere, orbiting one ordinary star. From there, the spacecraft would rise through the air, leave the pull of Earth, pass the Moon, cross the inner solar system, and move outward through the realm of Mars, Jupiter, Saturn, Uranus, and Neptune. It would pass beyond the planets, then beyond the Sun's protective bubble, where the solar wind weakens and interstellar space begins. Voyager 1 crossed that boundary in 2012, after 35 years of travel. But for a ship trying to escape the Milky Way, that would still be only the first step into a much larger darkness. The ship would still be inside the galaxy. It would still be carried through the same vast rotating structure as the Sun, which circles the galactic center at roughly 500,000 miles per hour. That speed sounds impossible by human standards, yet it is still only orbit. The Sun takes more than 200 million years to complete one trip around the Milky Way. To truly escape, the ship would need enough speed to become unbound from the galaxy itself. It would need to overcome the combined gravity of hundreds of billions of stars, clouds of gas and dust, the central region around Sagittarius A star, and the dark matter halo extending far beyond the visible disk. Near the Sun's position, that escape speed is measured in hundreds of kilometers per second, far beyond the speed of Voyager 1. That is why the journey would demand engines beyond anything currently flying. Chemical rockets could begin the climb from Earth, but they could never carry a large human settlement to galactic escape speed on their own. Nuclear pulse propulsion, fusion drives, antimatter engines, and laser sails all point toward possible futures, each one carrying problems of fuel, mass, heat, precision, radiation, and control. Then speed itself would become dangerous. Thin hydrogen between the stars, microscopic dust grains, cosmic rays, magnetic fields, old supernova remnants, molecular clouds where new stars are born. At ordinary speeds, much of this would feel nearly empty. At a meaningful fraction of light speed, it would become a constant environment of impacts and radiation, forcing the ship to carry heavy shielding. And because the ship carried people, it would have to become a world. It would need air, water, food, farms, medicine, schools, repair shops, power systems, artificial gravity, laws, rituals, and memory. The first crew would leave behind open skies, oceans, forests, cities, weather, and families. Their children would know Earth through recordings and lessons. Their descendants would inherit the mission as home, duty, and history. As the ship traveled farther, communication with Earth would stretch into years, then centuries, then longer. A message from 1,000 light years away would take 1,000 years to arrive, and a reply would need another 1,000 years to return. Earth's voice would become a voice from the past. The familiar constellations would dissolve. Orion, Taurus, Cygnus, Cassiopeia, and the Big Dipper would lose the shapes humans gave them. The ship would pass through the Orion Spur, through neighborhoods of red dwarfs, white dwarfs, gas clouds, dust, and ancient stellar remnants. Eventually, the bright disk of the Milky Way would begin to thin. Then the ship would see the galaxy from outside, a glowing spiral behind it, a central bulge, dark dust lanes, star-forming regions, ancient clusters, and hidden inside one tiny part of that light would be everything humans ever knew. Earth, the sun, the moon, every ocean, every city, every person who ever looked up and thought the Milky Way was the sky. But even after the disk faded behind them, the invisible dark matter halo would still reach outward. The final barrier would have no wall, no edge, and no color. Only gravity, slowly weakening until the ship's path no longer curved back. Then, at last, it would be free. The Milky Way would no longer surround humanity. It would shine behind the ship as a distant home, and the escape would be complete, successful, lonely, and irreversible.